Of course. You gotta do it. Okay, so hi, is this on? No. Hi. Good. Okay. So hi everybody. Thank you so much for coming, all of you. Welcome to Gopherfest. Today we're gonna have 4 talks. So you have there Andrew Duran and Rob Pike. I'm not really sure how to pronounce it. I'm gonna go Schlesinger, but no, good. Okay. And then Steve. First, about what they're gonna be talking about today. I wanted to first thank all the people that have made this possible. Organizing this kind of event with people and so actually not that easy. So I wanted to start first thanking New Relic for this.
We are so excited to have you here. Thank you so much for joining us tonight. We hope you enjoy the food and beverage. Hopefully you know about New Relic and our software analytics platform. If not, come find me and we'll have a nice little talk. Enjoy the event.
From O'Reilly, right? Yeah, thank you. I was gonna say something else now. Help us organizing, and they're gonna also help to go SF meetup.
Yeah. So what Maya didn't mention is New Relic is hosting an incredible party tomorrow night at Levi's Stadium. It's part of the Velocity Conference. So if you didn't and get a Google I/O, you should definitely come to Velocity. Visit the GoSF meetup page. There's more information about it. It's actually on there as an event. If you want passes, they're 30% off for this community, as well as there's free Expo Hall passes and 2 tracks of sessions from GitHub and other cool companies, along with access to all the great parties.
Cool, thank you. Thank you. Also, someone that was very important helping us getting this together, even though finally didn't work as we wanted, but I think it's gonna be awesome, is GoPro. And I just learned that not only they're writing open source software, but it's actually in Go. So,
hey folks, I'm Joe Bentley from GoPro. So we're really excited to join this event. We're just getting involved here in San Francisco. Really huge thanks to New Relic for letting us co-host this, and well, for them hosting and letting us co-sponsor this event. Google and Iron.io and the other folks. So, really excited to get back to the tech community. I've got a couple t-shirts here to hand out. If anybody wants a t-shirt, I'll throw it out here. Here's the first one.
that was fast. Whoa.
So, Zolfi in the back's got more t-shirts if you want one after the in between the event, in between the speakers or after the event, stop by. But thank you, Relic, the rest of the sponsors.
Yeah, thank you. You guys are hired. I think everybody anyway. Thank Google for my salary and for for helping us make this possible. So all the food and amazing beer is sponsored by Google. So thank you, Google. And finally, I wanted to thank also Hackalab. Hackalabs, they are actually recording every single Go SF meetup for a while now. They do a great job, and they're going to be recording all of these talks, and in around a week, it should be online. And also, today, this talk is actually, all this event is live on YouTube. So, thank you, Jason, for organizing this. That's why we have this small camera here. And I like to, so how many of you are from GoSF, like you come here regularly? Okay, wow, so many. So already, so how many of you have written Go before? And how many of you run Go on production? And how many of you make money out of it? Okay, that's pretty good. That's pretty good. And since today it's kind of a special day because on Thursday, Google I/O is starting, so there's a lot of people coming from different places in the world. How many of you come outside of San Francisco? Okay, how many of you come outside California, United States? Huh. I mean, yeah, Australia. There's actually some people coming from Japan, which I think is pretty awesome. Anyone coming from farther than that? Nah, okay, you win. Cool, so So I'm gonna stop talking now, and we're gonna have our first speaker. It's gonna be Andrew Duran. He works at Google. He works at the Go team. He was my mentor when I joined the Go team, and he's gonna be talking about the future of Go, Go 1.5, and what's coming after that.
Sorry, I have to do the old laptop switcher. Just so our viewers can watch it later.
Yeah.
Record?
Yeah.
Oh, no, now it's finished. Okay.
Yeah, we made that mistake once.
Yeah, this is the second time today. Sorry, everyone. This is fascinating, right? Cool. Whoa. That's the first time I've looked up. As you all know, my name is Andrew Durant, and I'm here to talk about state of Go, basically what's happening in the Go core at the moment, not in the community, just in the core. I couldn't do the whole community in 20 minutes, that would be impossible. This talk is kind of built on the talk that I gave previously at FOSDEM in February. So if you've seen that, I'm not going to repeat much of it. If you haven't, you can take a look at that to see what you missed. But primarily what I want to talk about is just Go 1.5, what's going to be in the next release. Go 1.5 is scheduled for August 2015, so I think it's the beginning of August. So the major work for 1.5 is already done. We're in what's known as the feature freeze period, which is just a 3-month period where we shake out any issues that might be in the release before we cut it. So one of the most major changes to the core is that the toolchain was converted from C to Go. So the old 6G, 8G, etc. compilers are now just one Go program called compile. The same for the linkers, they're now a tool called link. And there's a new assembler that's actually a totally new program. So Go 1.5 actually has no C code at all in the toolchain or the runtime, which is really nice. So you can bootstrap the whole thing from just having a working Go installation, Go 1.4 or above. But Rob is going to talk about this in a lot more detail, so I'll spare you. And so one of the marquee new features for you as users is the new concurrent garbage collector. And this is something that has been slated to be part of Go since its inception. We've always wanted to have a garbage collector of this kind, and now we actually have one and it works, which is great. So the goals were to limit pause latency to under 10 milliseconds. So the previous garbage collector was a stop the world mark and sweep collector. Basically, when a GC happened, while the GC is happening, your program is stopped. And so depending on the size of your heap and the type of allocations in your heap, you could be pausing for anywhere up to seconds. There were some people with really large heaps of many gigabytes who would have to endure really long GC pauses. But the new GC, it actually works by stopping periodically and doing just clearing parts of memory without actually stopping everything at once. So this explains the new process. Basically, normally while your program is running, the GC is off. Pointer writes go straight through to memory as normal. And then in parallel, I think there's a stop the world phase only here. So we do a stack scan to collect what things pointed to from the stack. We do a mark process, and during the mark process there are write barriers. So any writes through pointers are actually indirected through a piece of code that tracks changes made through those pointers. And then for a very short period, we actually stop the world and rescan anything that changed during this phase. And then we just finish the mark process, and then we resume your Go program's execution and then deallocate all of the stuff that's not in use. I'm doing a pretty bad job of explaining exactly how this works. You should watch Rick Hudson's talk at Gophercon to learn more about this. There's also the design doc at this URL, bellingdorf/s/go14gc. But basically, to illustrate the trade-offs being made between the old GC and the new one, we basically spend a little bit more memory and CPU time in exchange for much lower pause latency. And so in this old world graph, we have this is the garbage benchmark from the Go benchmark suite, and you can see here that the way the collector worked previously was with many stops, each of which were about 80 milliseconds long, in which the heap would have been scanned and collected. But now with the new collector, we still have many stops, but this time it's just these little peaks that are actually stopping the world. And so we actually only stop for about 1 millisecond each time we stop. And then we have this longer collection period where we're actually running concurrent to the user program, doing some of the garbage collection then. And so we actually run alongside the user program, which is what it means by concurrent. In addition to the garbage collector, we've also been doing work on the scheduler, and so we have better performance on when running across multiple cores. So if you set go max proc to the environment variable, the number of cores that you have in your machine, usually something like 4 or 16 or so on, what you'll find is that the performance is much better in Go than it's been previously. So these tables show various benchmarks running first with Go max proc equals 1, the default, and then 2, 4, 8, 12, and 16. And we see the comparison between Go 1, Go 1.4, and 1.5. And what we see is in Go 1.0 and 1.4, running the simple prime C benchmark, which is a program that calculates prime numbers, generating a lot of Go routines. Some of the work is parallel, some of the work is serialized, there's many channel communications and so on. In the original version of Go 1.0, it got worse the more cores you used, because Go routines didn't have an affinity for any particular CPU, so there was bad cache locality and things would thrash and so on. Go 1.4 got a lot better, particularly through the work of Dmitry Voyakov, who did some great work on the scheduler and made it quite great, so you would actually see improvement. Now we still see a similar kind of improvement in 1.5. But if you look at, say, one of the worst case examples, this chain example is just launching many Go routines and in serial passing a value through each of them. We can see that in Go 1, it just got a bit worse when you added extra CPUs. There was a jump from 27 microseconds to 300 and something. You'll see that it got a bit worse in 1.4, but not as bad. But you see in Go 1.5, it barely gets worse at all. It doesn't change an order of magnitude. It only goes up by a couple of microseconds from 36. And it remains stable. So our schedule is much more improved for not parallel kind of work as well. But if you look at, those are micro benchmarks, so they're only indicative of kind of special case behaviors. If you look at practical workloads like running make.bash, building the Go toolchain, or listing all the files in the standard library, or running the HTML template tests, you can see that we actually see practical improvements by setting Go max procs. So make.bash gets a bit faster, but it was already using multiple cores to build packages anyway, so that's why it only gets a little bit faster. Go list is actually a mostly IO-bound operation, and you'll see that it just gets a little bit better, but only marginally. And running the HTML template tests, we do see an improvement, but that's not a particularly parallel operation either. And in general, in our benchmark suite, everything just gets better. So bottom line is Go 1.5 works better on multiple machines, which is great, significantly better. This is just a graph that talks about Go Go 1.5's performance against Go 1.4 across all of our benchmark suite. So the vertical axis is the geometric mean of performance of all of the benchmarks together. And it goes back to mid-April when a bunch of the concurrent GC work had been in the tree. Things were a bit worse. We added a few more things. Disabling debugging somehow made it worse. We don't actually know why. When we introduced multi-threaded concurrent GC and changed the way the garbage collections are triggered, it got worse again. And then we fixed a failure where the GC wasn't triggering, and so it got slower again. But then work was done to improve caching of GC work, to improve the write barrier code, to improve the scheduler, and to fix a bug. And now we're actually back up with, on average, than we had in 1.4. So it's not significantly better than 1.4 in general, but it's slightly faster or the same. And we can actually see our entire benchmark suite here. You can see all of the things, most of which got slower, some of them dramatically slower. Most of which got faster, some of which dramatically faster. It's a binary thing. It's just a bit flipped in my brain. Yeah, a lot of the regular expressions, one of them got a bit slower. But you can see that on aggregate, things are more or less the same, if not better. Okay, so that's performance. Go 1.5 has some new operating system and architecture support. We now can build on iOS devices, so Darwin ARM. Also, there's ARM64 support, so we can run on 64-bit ARM cores, which includes the newer iPhones and iPads, and also some of the server-grade ARM machines that are out there. I think there might be some ARM64 Android stuff, I'm not sure. Anyone know? I don't know. Yeah, we also support Linux on ARM64, which has Sega, which is nice for the servers, and we support ARM on OpenBSD, which I think is still in its early stages. We retired support for Dragonfly BSD on 386 because they dropped support for it, and similarly, Apple doesn't support OS 10.6, and so we made the point not to support Snow 11 anymore. Which doesn't mean that it doesn't work, although I think at this moment it doesn't work. It just means that we're not going to try hard to make it work. And a significant feature is shared library support in 1.5. So it means that you can build Go libraries as shared libraries and then link them from Go programs. So if you run Go install with build mode equals shared, you can build the standard library as shared libraries. And then you can build a Hello World program that links against those shared libraries. So I can give you a demo. Here I have a Hello World program that just does that, imports the funct package. In my package, Linux shared, you can see, oh, what? No? Oh, no, it's not called shared, it's called. It's not going to work now. Let's see. I should be able to build with build mode equals shared the hello.go file. Okay. My demo, yeah, I actually did this demo just before I got here. Anyway, you can see that if I had done it, that's what would happen. And you get a 13K Go binary that links against all the objects, which is quite nice. So the prime, I don't envision really using this myself, but I know that part of the work for doing this has been done by an employee of Canonical, and they have an interest in packaging Go programs for Debian and Ubuntu, and their packaging guidelines require that each dependency is packaged individually. And so this actually enables them to individually package each part of a Go program and not duplicate not duplicate libraries that are used by multiple things. So that's quite nice. You can learn more about those execution modes with the design document. Also included in those is the ability to build C archive files and shared libraries. And so you can build a Go program or a Go library as an object file that you can include from C programs. So if you have a package P, you just put a CGO import statement here, just importing the package capital C, which is a package. And then you put an export comment of the functions that you want to be accessible from C. And then you write a main package that imports that package, and the main function is just ignored, so you just leave an empty main. And then if you run go build with build mode equals C archive, you get object files and a header file, which you can link to from C programs. And so when you link against that code, when the C program starts, any of the init functions in your Go code will be executed in the package's Go code. But the main will not be executed. But then you can just call into these functions. And so Go code can now be called into from C. That's quite nice. And that's used on mobile as one place it's used, and I can imagine a lot of people have uses for it as well. If you want to add Go code to some legacy C projects, for instance. There is a minor language change. You can now omit the key type from a map literal. So if you have a map that points to some value and point is a struct, previously you had to write it like this, and now you can just write it like that. So you know, that's serious business. The Go tool used to have a Go doc subcommand, and all it would do was show you the package documentation for package. But now it's been resurrected. It was removed in 1.4, and it's been resurrected for 1.5 and re-implemented as a nice command line interface to GoDoc. So you can say GoDoc and then just the package name match against all the packages in your Go path and find one that ends in that package name. And it doesn't match on case sensitivity, so you don't have to get the case right all the time. And if you just put, if you just give it a name on its own, then it will look in the current package in the current directory. So, for instance, you know, I'm in this package here, package audio. If I say GoDoc, I get the whole. I'm going to find out more about the engine type. I can say GoDoc engine, shows me the methods on engine and the documentation. And you know, if I wanted to learn about funct.print, you know, I can find it there. So that's quite nice. There's a new execution tracer in Go 1.5, which allows you to, it's basically like a heavy-duty profiler that basically writes out everything it does. It doesn't use simply sampling as the old one does. It actually logs everything. So your program runs a bit slower, but then you can use the, there's this trace viewer that was done by the Android and Chrome teams, and it lets you generate traces like this in a user interface that you can navigate. So you can, here I'm GC, and I'm looking at the GC characteristics. This is with the old, this is not a newer one. So you can see this will improve. But then you can see four threads running across CPUs and all of the Go routines executing on those. You can click through and see what's happening. So this is going to be really useful for understanding Go programs. So yeah, you can learn more here, go.org/s/go15 traits. Of course, we have more analysis from refactoring. Some of these listed here have been around before, like the Oracle, but now for Sublime Text and Emacs, so that you can, you know, and navigate source code and learn more about, you know, where a particular identifier is used, or, you know, if you have a channel, you can look at what values are sent on that channel and so on. GoDoc also has some of that magic in it. You can run GoDoc with pointer analysis, why I can see all those details about how code is used. So it makes the Go documentation a lot richer and the source code view a lot richer. And we have a couple of refactoring tools, which there's a lot to say about them, so I won't go into them now because I don't have much time, but they're definitely worth taking a look. They're all in the Go tools sub-repository. Brad and I and a few other people have been hacking on the continuous build infrastructure that we use for testing Go across a variety of platforms. It's now running Linux, Windows, OS X, FreeBSD, OpenBSD, builders all on Google Compute Engine. So when someone commits a new change to the Go core, we actually spin up machines to run builds across all of those platforms. And so we'll spin up like 20, 30 instances and build, and then just shut them down when they're done.
OS X is it on computer?
Oh yeah, so OS X is running in a kind of different way where we have a bunch of machines that connect to our build coordinator, and they say, I'm available for builds. And are we using VMware on OS X? Is that almost? Almost. So at the moment we're just doing builds on those machines, but we plan to actually spin up OS X instances inside VMs on those OS X machines. It'd be nice if Apple let us virtualize that somewhere else, like on a cloud product, but we can't. And for doing builds of on Android devices and on iOS devices, we actually have a bunch of those devices plugged into a bunch of machines running that same software, and we farm the work out to them as well. And the nice thing about doing it this way is we're able to shard the execution of tests across multiple machines. So when we're dealing with slower hardware, where our test suite would normally take a full hour to run, say, we can actually split it up into like half a dozen different stages, and give tests A through N to one group, and L and so on to another group, which is really nice. And that also enables us to more practically do try-bots, where we can have a pending change and test that it works. I'm actually going to do a little hacking on some of the Go build process now, because it's a good time to do it, I guess. So here's put something in main. I don't know why it's called X main. In fact, it doesn't even have to be real Go. That'll do. Yeah, I think that. Yeah, that'll work. I'm sure. I'll send it to Russ. Oh. Pre-submit checks. All right. Fine. Editing my code. All right. And I'll mail that to Russ. So this is uploading the change to our code. I can open this URL in code review system and see my change. Great. I'm going to click this run trybot button and post that. And then within, I don't know, a short time, we should see some change. So I can actually see this is the farmer's user interface, well, status page, which is saying that it's trying my build, and that's running on a Linux ARM. That can't be right. This couldn't have got that far. Brad says I should just ship it. It hasn't kicked in yet. Come on. Yep. If one of my demos works, I'll be happy. This one doesn't work.
It only looks every like minute for new ones.
Well, I can come back to it anyway. I don't need to. We don't need to see it happen right now. Oh, here we go. Trybot's beginning. So now I can look at that status page. This is the trybot status. One's already failed. The Darwin one has failed. yeah, it looks like they're all doing badly. And now I'm seeing more info from it says it failed on Darwin MD64. It's not going to tell me about each one that fails. And then it's just got to wait for them all to fail before I get the final report, which should be soon. 13 builds remain, 12. The nice thing is you can actually see streaming build output from the machines, I mean all of them, as it happens, but it's already command not found. 7 builds remain, and so on. Anyway, when that's all broken, it will tell me that it's bad. What does Brad say? Never mind, this broke the build. And I will abandon. Don't know what I was thinking. All right. So that's really useful for us because often you'll make a change and you won't know. You don't have time to manually test it. You want to test it across everything. And finally, mobile. So 1.5 supports good support for Android and experimental support for iOS. So this is, I don't have an iOS device. Well, I have one, but I don't have one that I have the dev stuff set up for. But this is it running a Go program. I got a colleague to send me a photo of that, so it's real. It's not faked. You'll have to take my word for it, I guess. But one of the nice things about the Android support is that we have this Go mobile tool, which is like the Go tool but for doing mobile development. And who here has set up an before? And keep your hand up if it was easy. All the hands went down. Oh no, one person kept it up. But yeah, it can be a bit confusing and difficult. But to set up the Android, I use type Go mobile in it, and it downloads the Toolchain, everything, and sets it all up. Not for doing general Android development, just for doing Go and Android development. And then once you have a Go mobile app, you just run Go mobile install to build the APK and upload it to your device. So the workflow is very similar to just writing normal Go programs. And also there is the Go mobile bind command, which lets you build a shared library that you can use in a Java Android app or an Objective-C iOS app. So you can, if you want to write your networking code, Go, so that's quite nice. Network libraries and Go routines are a great way for writing network code. You can do that and still do all of your UI work in Android and so on. In Java or Objective-C. But so I can give you a demo of this. I've written this Flappy Gopher, which is not a full game, but this is the source code. People like it when I turn on syntax highlights. I've learned. It only took 5 years to realize that. But, basically, I have an app with I'm not going to try and explain the whole API, but I create an app and run it with these two callbacks, draw and so the draw function, it sets some GL crap and renders the scene, which is set up somewhere else. Has anyone done OpenGL programming? Would you agree that it's GL crap? Is that just, yeah. And then I have something that calculates the position of things and then handles touch events. There's a lot more to say about that, but I don't have time. So if I run go install locally, it builds a version of this that actually runs on my local machine. So you can see that basically it's like I'm supposed to avoid this thing. I don't know why it's so big. It must be the resolution of the display. It's supposed to be much bigger. But if I plug my device in and then make sure it's switched on and run Go mobile install, please give me my last step. So you can see it's running, it's linking, now it's running ADB to upload, and yep, it's done. Now I have this main icon here, and I tap that, and I have my Gopher running on the thing. So that's the kind of, write compile test cycle that I like to see. So I'm very excited about that personally. Finally, I just wanted to talk a little bit about the Go community events that are coming up. There's GoCon, the organizer which is here, organizers, and that's in Tokyo next month. Is anyone going to that? Apart from you guys. Yeah, Francesca's speaking there. There's also Gophercon in Denver. Who's going to Gophercon? Way, that's cool. It's like a quarter of you. Great. And Goth and Go is in New York in October. Anyone going to that? Why would you go over there? You might. Yeah. Why not? I don't know if there's a real East Coast, West Coast thing. I really don't. I'm Australian. I don't know. And also there's another .go as there was last year in Paris. And I know there's at least a couple more significant events that are going to be announced. All right. Thank you very much.
So I think we have some time for questions. So if you have a question, raise your hand and someone will bring you a mic. That someone being me, actually.
What are the Go mobile plans?
What are the plans?
Like longer term? That was a cute demo, but is it?
Just to kind of continue down the trajectory that we're going now, to build some nice libraries for basically building games. Some of the libraries that I used there were a sprite package, and there's also an audio for doing just cross-platform 2D and audio stuff, and handling touch events and all that kind of stuff. Just basically getting that to a nice sort of polished state, and then I guess we'll see where we're at from there. There's no kind of like massive overarching roadmap, but you know, particularly in speaking to people who are kind of in the game sphere, and also people you know write libraries for apps, we know that people really want to use Go, so we just want to make that possible.
You might want to also talk about the other side of it, like the Go buying side, keeping your UI in Java.
Yeah. So like, so you know, if you write Java apps or iOS apps, the chances are you want to include some Go code. Maybe you want to share some code between your server side and your apps. If you write that code in Go, we want you to be able to use that on those platforms. And so a lot of the work involved there is really just finessing that whole process with like the Go mobile tool to support iOS in the same way it does Android now. And we think that's a nice thing to have, and that's what we're shooting for. All right.
Question about
Hey, with respect to the library, the shared object loading, are they sharing, if you load two libraries, do they share a scheduler so you can pass things between them on channels?
That's actually a good question. I think if you use the shared object mode, you do share the same Go runtime between different Go shared libraries. But if you use the C archive mode, where you basically build an entire Go program that's linked, I think you don't. But don't quote me on that. It might be the same in both cases, in which both get separate runtimes. Yeah.
So the Go mobile stuff is super awesome. Do you have plans to integrate or like separate some components so you can use it in a more embedded sense?
You mean using it on not mobile platforms like other?
Like nice here, it runs Android, but it also runs embedded Linux, and I like embedded Linux because it's a little bit leaner and I can do more stuff like 4K processing. And I'd like really like to use Go, like if they're on the mobile stuff, or embedded use case.
I mean, if you're talking about embedded in the sense of something you can run Linux on, then you can already probably run Go there. And particularly if it's an ARM, you most likely can. For MIPS and stuff like that, you can use GCC Go. But as far as like for doing embedded stuff, I know there are people that have done like GPIO libraries for doing I/O on pins and stuff like that. And so there are already people doing that kind of work. So what you want may already exist.
There's a couple of Googlers who are writing a cross-platform GUI library in Go. Is that going to be announced in the 1.5?
A couple of Googlers are writing one.
Yeah, it's looks like a cross-platform GUI library in Go.
It's like Android OpenGL debugger people.
Oh, right. I'm dimly aware of it, as you can tell, so I can't say anything about their plans.
Okay, so we're going to continue. Thank you, Andrew.
Thank you.
And next up, it's Rob Pike. I think you know him already. And he's going to be talking about why Go's compiler was written originally in C and why it's not the case anymore.
You're asking. All right, we'll try. Okay, that was fine. Did you start? Yeah. Going. Doing something every day. Hi, thanks, Andrew. I'm going to talk about a specific point that Andrew talked about, which is that we got rid of all the C code. It's not that we don't like C. I've probably written more C than any other language out there. But there are reasons to get rid of it. And it was also a really interesting process, mostly what I want to talk about. So as Andrew said, as of the 1.5 release, the entire system is written in Go. There's also some assembler, but not very much. The point is C is gone. There's still C Go, but outside of that kind of thing, there's no C in the runtime or the toolchain. Now I'd like to just stress that I'm talking about the GC compiler now. GCC Go still is written in C++ and uses GC, whatever the GCC library is. I forget the name of it now. That's still going strong. So it's not a general replacement. Although I suspect the runtime work that we've done, a lot of it, which is in Go, will be bound up into GCC Go at some point. So the first question is, why was it in C in the first place? This is a question a lot of language experts ask us, because it's well known that what you always do is you write the language in itself. We didn't do it because we wanted an easy bootstrapping process. If Go doesn't exist, it's very hard to run the Go compiler. And so it's easier to take an existing language like C, or for GCC Go, C++, write the compiler in that. Also, there's a subtle effect. If you write the language in terms of itself, the language becomes a language suited for writing compilers especially. And although that's an interesting thing, it wasn't really what we were after. So we didn't really care what the language was it was written in. But at some point, it became harder for us to maintain the C language and the Go language side by side. We want to just move it to Go. So why move the compiler? As I said, it's validating our work. We have very and they're simple. Go is easier to write than C. Go is easier to debug than C. Also, if there's only one instead of two, it's easier to get contributions from the community, and that's already happening in much faster than it did when it was a C language compiler. Go also has much better modularity. To say that C has any is a bit of an overstatement. And of course, we've got the awesome tooling that comes with Go, which we can use to improve the compiler and work on it. There's actually unit tests for the compiler now. Imagine that. And also, a point that is actually relevant is Go makes parallel execution trivial, so you can imagine running the compiler in parallel, and that's actually something that's sort of happening. And so we're already seeing these benefits, even though that it's only really been working for a couple of months now. And there's a design doc called Go 1.3 compiler, which the announcement was made around 1.3, although we knew it would be a few releases before it really got done. But it's not just that compiler that moved, the runtime moved too. And so we had actually our own C compiler to run just for writing the runtime for Go. Now, it wasn't a C compiler from scratch, it was essentially, although not exactly, the Plan 9 C compiler. And we needed one because we needed our own API so that we could do things like have the segmented stacks work when Go called C through the runtime, have that break. So it was a very sort of subtle problem having two languages coexist. Owning both compilers, the C compiler and the Go compiler running in the same world, made it a lot easier to manage it. So it's actually a really good idea for us to do this, but of course we had this weird extra C compiler that seemed strange. We couldn't use GCC to do that. And so this process is converting the runtime to Go means you can delete an entire compiler from our toolchain. And that's a huge deal, right? Compiler, no, nice. And of course, all the reasons I mentioned on the previous slide work for the runtime too. You can have tests that work better, and profiling, and so on and so on. And so now there's only one language we have to maintain, which means there's only one set of stack management software we have to write. There's only one set of data management and this kind of stuff. It's much, much simpler. And as usual, when I'm giving a talk, it's all about simplicity. Comes up though in this, which is why did we have our own tool chain at all? Why didn't we just build everything on top of something that was already out there? And that's a pretty good question. We even considered using LLVM for about 20 minutes in the early days, but decided it was just too slow. We wanted a fast compiler. But we had our own reasons for having our own API, which are involved with things like how the stack gets laid out and how to do Go routine switching and this kind of stuff that's sort of integrated fundamentally into some level of the compile world. And so we just took what we were familiar with, which was the plainline tool set, and not exactly, but to some extent brought it over and made it work. And so because we were familiar with that, we knew how to work on it, it's actually very small compared to like GCC or LLVM, we could move quickly with it. And that was, I think, as Russ once said, if we'd started with LLVM, we probably would have not gone very far. Not that there's anything wrong with LLVM, it just doesn't have our goals in mind. There was last year a rather rude blog post complaining about which I won't go into in detail, but Russ wrote a very thoughtful response to it, which is worth reading because he explains these issues in great detail, and I think did a really good job, better than I can. And so as a result of moving to Go, we can now do things that were not really possible, I mean literally not possible before. For instance, we completely re-architected the linker. We put in the new garbage collector that Andrew talked about and that Rick will talk about at length at Gophercon. And that includes things like stack maps, which are a way to track what's live pointer data on the stack. The new contiguous stack work. We used to do segments. When a stack grew, we allocate a new block and jump to that and then jump back when you return. Now, if we hit the bottom of the stack, we actually allocate a whole new stack, copy the data over, update all the pointers, get all that right, run on that new world. And that's a pretty big change. And then the write barriers that are necessary to have a concurrent garbage collector. Three things are actually pretty close to impossible to do if there's C in your runtime, because C is not type safe. You don't know whether a word is a pointer or not. It might be a union that's a pointer sometimes and a floating point number on Wednesday. You just don't know. And there's also lots of aliasing that goes on due to optimizations in C programs, because the compiler can recognize that this cell in this part of the function can have one type, but I can reuse the cell down here. And that kind of stuff is very difficult to follow. You can use stack maps to help you, although it's hard at C. But for instance, to the C compiler of any stripe is a very big deal. And now that we don't have a C compiler to worry about, that whole problem just vanishes. So that's tremendous. And sort of proof of the pudding is we expect that GCC Go, which is written using the GCC backend, will probably have segmented stacks and imprecise stack data collection for the foreseeable future, essentially. Maybe one day, but not anytime soon. So what about those stacks? Well, in 1.2 up to 1.2, stacks are these segmented things. Then in 1.3, that's the time we decided we wanted to make this move. We had to plan the new garbage collector, the new compiler move, and all this other stuff. And so the first thing we did was Keith Randall suggested just making these contiguous stacks. But you can't do contiguous stacks with C code because you can't move the stack data because you don't know what's a pointer. So the first step was to implement contiguous stacks unless you're in C code. So when C code is running, you actually go back to segmented stacks. So basically in the runtime, sometimes you were in contiguous stacks, sometimes you weren't. Then in 1.4, we pushed harder on this and made the stacks contiguous by restricting where C could run to be only on the system stack. We literally jump stacks when you're going into C. So that was cleaner. And then for 1.5, well, you get rid of C code, problem goes away, and now we always have contiguous stacks. And that's more efficient and just much better, and also helps the garbage. And also, independently of converting the compiler, we had to convert the runtime, which of course where the stack work happened. And that was mostly done by hand with machine assistance. And the tricky part is writing the runtime in a type-safe language, which is pretty much breaking a rule. And the way you use essentially the unsafe package and maybe a couple other tricks. For instance, you have to, in the garbage collector, look at a pointer value as a bit pattern in order to be able to do things like set mark bits and that kind of thing. And so you have to use unsafe to do this. It turns out, though, there's much less of that than certainly I expected was necessary, which implies that we had the right kind of tool set for doing this kind of thing. Even though Go is type safe, we have a really good escape valve that's just kind of the right shape to make things possible to write a full runtime in this type-safe language and only cheat when we really have to. And also, to convert the runtime, there's a lot of code to translate. Some of it was done automatically, which I'll talk about now. So the biggest job, the biggest single job in all of this probably, was converting the compiler from C to Go. Now, you might think, well, why did you translate it? Why didn't you just write a new one? And that's a very good question, and it doesn't have a simple answer. For instance, we could take the Robert's Go AST and parser and so on, build that up, write a new backend or couple to the backend. And there's good reasons for doing that and good reasons for not doing that. But we decided to go with a strict translation for now at least, primarily for correctness. The C version of the Go compiler is a big program. It's actually about more than twice as big as the C version of the C compiler. And it's got a lot of subtle things that we've tracked down, bugs we've fixed, semantic details we've worked on, and we know that those work. And if we can translate the code and produce an identical program in a different language, we just have a lot less to worry about. We're not going to introduce new subtle bugs in this process. And so we decided to translate it, but of course you don't want to translate it by hand. That's annoying. So naturally what we do, it's sort of our full-time job, we wrote a program to write a program. And so Russ wrote this custom translator that turns C into Go, and then you run that translated program to get the output. You run the compiler that results, which is now a Go program, but it's still a Go compiler. It should generate exactly the same output because it's the same program, just in a different language. If it doesn't generate the same program, you have a bug, you track down the bug and you fix it. So you iterate until you have two versions of the compiler that generate exactly the same output. And then you know you have a correct Go compiler, even though it's machine generated. And then the result, of course, is really bad code because it's machine translated. But then you can sit there using the awesome tools that we have to work on Go code to make it much, much nicer. And that's still going on even today. So the translator was done by generating this line-by-line translation. And I can't go into the full detail. Russ talked about it a little bit at Gopherfest last year, but it's actually turned into quite a different thing than what he talked about. It's a little bit different. I want to stress that this is not a general purpose C to Go translator. That job is just too hard. We had a very specific program written in C in a certain style by a certain person, Ken, and we knew how to translate that dialect basically, but the general dialect is beyond this tool. So the first thing you do was parse the C code. Russ had a Yak grammar in his back pocket, kind of thing he carries around with him. And we translated the C program into a parse tree. Fix anything that you can't represent inside Go. An example is star P++ used as an expression. In Go, star P++ is a statement. And so you do what rewrites you have to. Now you have a C parse tree that's been simplified to Go, if you like, but it's still a C program. Now you print it as a Go program. So you just change the syntax when you print the tree. It's actually pretty easy to do, relatively speaking. Now you have a Go program that's a Go line-by-line translation of a C program into a Go program. Compile that and then do the cycle I talked about on the previous page. Now the parser for the compiler is written in Yak, and that was actually hand translated using Sam to do most of the heavy lifting. So that wasn't running, but it's a relatively small piece of the thing and much simpler to do. So the translator sort of automatically can't do absolutely everything. It needs a little bit of help. And so there's a sort of configuration thing that sits on the side of the translator that tells you things that it might not be able to intuit easily itself, like this bool even though it's declared as an int, because C doesn't have bools, at least old C doesn't. Or this function returns a bool. And then for more complicated things, like recognizing that this pattern is better done by calling on the standard library, there was a kind of diff-like syntax for generating these matches. And in this thing here, you can see it's in C code, because at this point, you have a C tree represented in Go syntax. So this is what the tree looks like in Go code now, and you can replace this wretched stuff with a call to make, or a couple of calls to make. As another example of these kind of diff rules, this one, C basically doesn't define what shift is. It's just very confused. But in Go, they're very rigorously defined. And so you can take this fairly messy C program to make sure you get the right answer always, even when C doesn't tell you what's going to go on. You can replace it with a simple shift because Go is better behaved in this respect. And so there's a bunch of these configuration things which typically generated by finding a bug in the output or a bad piece of code. Once you have this working, you now have a Go program that looks like a C program that's been translated mechanically. And so now we can bring the tools of Go on bear on fixing it up. And so Russ, again, wrote this tool called Grind. I don't know why it's called that, but it did a lot of grinding. I guess it ground the rough edges off. And it now is in Go. So it can parse the Go program results, do type checking on it, and then writes down a list of things it wants to change. What it does not do is edit the parse tree, because it's kind of hard to edit parse trees. It's annoying. It's a clumsy thing to do. What this thing does instead is represent everything as source text, but parses it to see what to do. Writes down a list of source edits, like on line 27, move this line down one or something like that. And then when he prints it out, he executes that edit chain to generate new source code. So it's actually a source-to-source translator, but not by manipulating the parse tree. And the changes that it executes are driven by various analyses and a lot of staring at the screen. Things like removing dead code and unnecessary go-tos, getting rid of labels, indirections that don't need to be there, and stuff like that. And then one I'll talk about quite a bit, moving var declarations around, which turns out to be really important. So this was the big tool for fixing up the crappy code that came out of the translator. Now, what happened was the first time the translator generated a work and we ran it on a real piece of code, it was using the HTML template test suite as a test case. It was 10 times slower than the previous compiler. Not because Go is intrinsically slower, but because the code was so terrible, right? But the question is, what's wrong with the code that comes out? And we actually learned quite a bit in understanding slow and speeding it up, most of which we've gotten back now. It's still a little slow, something like 10x. The main thing is a combination of things that C does differently from Go. For instance, in C you tend to write really complicated for loop conditions. It doesn't do that very well. And so what the translator would do is if there was a complex for, it would put it inside a closure, because that's the easiest way to get a single expression to be a complicated thing. And so all these for loops in the compiler were turned into closure runs on the iterators, which was really expensive relative to a regular for loop. So we, by hand or mechanically, would rewrite those complex expressions to make the code more Go idiomatic. A really important thing is that on C, by definition, because it doesn't work, variables on the stack never escape to the heap. By definition, the stack is just the stack. There's no moving back. And so if there's a variable on the stack in the C version of the compiler, you know that does not escape to the heap. By the time it becomes a Go program, the Go compiler might not understand that. And so things get put on the heap that don't need to be, because semantics is hard to figure out for the automatic translator. And that caused some slowdown because things got moved to the heap that didn't have to. There are interfaces that hide some of this heap escape possibility, like the way func.stringer works versus the much cheaper var args in C. Not intrinsically cheaper, but in practice. And then there's things like the lack of unions in Go. The C compiler has this massive union in it to save memory. And there are no unions in Go, so that became struct, which made it bigger, which made it use more heap, which hurt the cache, and so on and so on. To squeeze some of those structures down to improve the density of the memory. And then probably the most important single thing, variable declarations were in the wrong place. When you enter a C function, and we're talking old C, C89, NCC, you always put all the declarations for the function right at the top. Opening brace, here, int I, char star p, whatever. And in the compiler, there were some very, very big functions, like the walk that walks a tree repeatedly. And it's a massive block of declared variables. But on any given call to that function, only 2 or 3 of those variables might get used. But every time that function is called, Go would say, oops, do escape analysis on this function and push all these variables out to the heap that weren't even going to be used, let alone need to escape. And that was a major cause of GC overhead, bloat, and so on and so on. And so one of the biggest things Grind did was turn that big block of declarations at the top of a C function now in Go and broke it down into moving the variables to where they're actually used. So the variables only get allocated and created when they're needed during execution, not every time every function is called. And that was a huge speed up doing that. Another way to think about this is that the C compiler doesn't ever free anything to it, pretty much. It's not literally true, but it's pretty much true. It just allocates stuff because it's got a finite run, it's going to be finished, doesn't have to maintain anything. And so it doesn't have basically no allocation Whereas the Go, there's a garbage collector, and it doesn't know that the compiler is going to complete. That's called the halting problem. And so it has to assume it needs to collect memory. And so the garbage collector provides a certain overhead here that is just unavoidable. But of course, we're working hard on making the compiler better. But anyway, this was a lot of interesting technical analysis about how C and Go are fundamentally different languages in a lot of surprising or not so surprising ways. So we fixed a lot of these things pretty easily. We moved variables closer to where they were first used. That had a huge effect. We'd also take a variable and make multiple versions of that variable through a function in order to allocate them only, uniquely for each place. We find places in the compiler where a library routine, which was optimized heavily, could be used instead of some generated Go code that wasn't very good. Somewhat related, but not exactly, we replaced the multi-precision arithmetic that was inside the compiler for doing expression evaluation for constants, and replaced that with a package, which is a very efficient and correct, it turns out, implementation of multi-precision arithmetic. We use some tricks to make the structure fields collapse. We sort of simulate unions using interfaces, which adds a certain computational overhead, but it's a win because it reduces the memory somewhat. David Chase, a new member of the team, has been doing much better escape analysis so that the difference between what the C compiler does and what the Go compiler does is shrank significantly. And then, of course, a lot of hand tuning and data layout and profiling and so on and so on. And much of this was done by automatic tools like grind I mentioned, but also just Gopherfest-R and the new tool, EG, that Alan Donovan wrote for doing a lot of this work. As a surprising example, while I was working on something I'll talk about in a minute, I wanted to simplify some debugging prints inside the library that the compiler, the linker, and the assembler use. And to do this, I actually got rid of an interface and an argument and replaced it with just made it be methods. So it's a print method instead of a stringer, if you like. And this is only used for, it was never called in a typical compile. But when I made that change to a library, the compiler sped up 15%. And the reason is that because it might be called in debugging, the compiler's escape analysis decided it's going to an interface, we don't know what it's going to do. All these variables have to keep, and it was a fundamental data structure that was escaping that didn't need to escape. So totally by accident, by fixing a print routine to simplify it, I made the compiler 15% faster because our escape analysis has got no ways to go yet. And there's tons more to do, and this work is ongoing. So technical benefits of doing this, besides the ones I mentioned, probably the single most important thing that's true now is that because there is no C code, no contributor in the community is going to submit a dangling pointer bug to the repository. That's a huge win. But also, in doing this, it gave us a chance to clean up the backends. We did a major refactor. I'll talk about a little bit more in a minute. Really cool is we've now unified two of the architectures. So the 386, 32, and 64-bit architectures are now really just one inside. So that just reduces the amount of code and complexity. That was kind of neat. It's now much easier to install a new architecture for a variety of reasons. One of which is that you don't have to worry about the C compiler. And we also, in the process, have now unified the toolchain. As Andrew mentioned, there's now only one compiler, one assembler, and one linker. So now when you want to compile, normally you just use go build, of course. But if you're not using go build, you're running it by hand, perhaps from a makefile. You just say go tool compile, and you change the architecture and the operating system just with the standard goose and gorge, as they're officially pronounced. And so you just normally would say go tool compile, link, that kind of thing. So now there's only one compiler. It's a single binary. And that program's job is to compile Go program into the target architecture and target operating system as defined just by two environment variables, which is a little simpler than, I think, porting in some other systems I know. And so 6G and 8G, they're gone, 5G, 9G. You just have one compiler now. And that compiler, this process, well, not the end, but where we are now, is about 50,000 lines of portable code. And then, but because of this refactoring that was made possible to the Go tooling being available, we actually made a lot more of the code portable than used to be. So there's a lot of duplicated code in C that was very hard to unify, but in Go it was a lot easier. So for instance, although there's only one compiler at multiple architectures, there's only one registerizer. The registerization pass of the compiler is purely portable code that's controlled by simple configuration that's part of the architecture definition. So it's actually a kind of cool thing. There's a little bit of non-portable code. It's typically around 10% of the size of the portable part, so a few thousand lines. The x86, of course, more than some of the others. But the tricky parts include things like people optimization and knowing things like this register gets written over if you do a shift and that kind of thing. But for the most part, like 90% of the code is completely portable. And that also, of course, makes things much easier to work on. There's also a just for fun, I wanted a project, so I decided to write an assembler. Rather than, we have translate assemblers, which I referenced when I was doing the work, but now there's just one assembler. It's entirely written in Go, and of course it's therefore a lot nicer code to start with. It's only about 4,000 lines, of which again, actually quite a bit less than in the compiler, relatively speaking, is machine dependent. And it's also, with a couple of minor tweaks, completely compatible with the old one. So it's again a complete move to Go with the existing tool. What's interesting, if you think about it, when you're looking at the compiler, the input language is the same, right? You always have, func, printf, and all that stuff. The assembler is not a language you think of as a portable input language. But guess what? It is. And now, this is one of the things where the guy who blogged about me being a jackass really missed the point. The assembler syntax that Ken wrote, defined back in the Plan 9 days, and looks like a 68,000 no matter what your architecture is. That seems annoying to people who love assembly language. But the fact that it's actually a portable language means that you can like this, have a single assembler in a few thousand lines of code for all the architectures in the world. And if you want to add a new architecture, it takes you very, very little time. And I'm going to tell you a lot more about how we do that in a minute. And it's totally an accident of the kind of history that Ken is responsible for, which is having an idea really early on, but 20 years later you go, that's what he was thinking. And so there's also this unified back-end logic, which is a single library with a single API for all of the architectures. So it was actually really fun to write this program and think about how different it was from the way people usually think about assembly. And then, of course, there's the same thing after the linker. There's now only one linker, no 6L, no 8L. This was mostly done by the translation tool, a lot of hand-to-hand combat as before. It was actually the first part moved, I think. And part of it was hived off into a library called internal/obs, or just obs, which is basically the back end of the linker. And it does instruction selection, knows how to format instructions, generate object code, all that kind of stuff. And if you look across all of the machinery now, there's about 27,000 lines of code there, which is fairly big, but it includes the definition of the instruction sets for all these machines. So it's quite a bit of stuff. But now, this was related to my 50% speed up in the compiler that I was responsible for. There's now one printf. So anywhere in the toolchain, you can print out a node, or not a node in the compiler sense, but the linker sense. And it'll print out the instruction in a standard, what we call portable assembler format. So it's just one subroutine to do all that. So it's the kind of thing you get when you unify. It's really nice. Now, there's a bootstrap problem. There's no C compiler anymore, and I want a machine that doesn't have any Go compiler. How do I boot? Well, the answer is go get a Go compiler. Just go download one. That's the way to do it. And so basically, you need a 1.4 compiler because the 1.5 port depends on a couple of features of 1.4. And we'll try, I think, to keep relatively close to that. So you grab the 1.4 build as a binary, just download it from the website, put it in a Go 1.4 directory, and then you can build from source the 1.5 and all the following guys on. It sounds a little onerous. It's actually not a big deal at all. You can read about how it works at the Go 1.5 bootstrap site. So what's the future? Well, there's still a lot of work to do, but we're pretty much frozen for 1.5. So we probably like the compiler to be a little bit faster. It's still a little slower than it used to be, but we don't want to make big changes now when you freeze. So it'll get faster later, but it's done now. It all works. Everything we've talked about today is real. But there's much more to do down the road for 1.6 and after. We're going to do better escape analysis, which has a huge effect on performance, be better garbage collector stuff. There's a new compiler backend using static single assignment that Keith Randall's working on that'll make it possible to do much better optimizations in the compiler, which have a huge effect, doing things like sub-expression elimination, eliminating index-bound checks, and that kind of thing. And this is the kind of thing that, now that it's in Go, you go, oh, this is going to be easy now. Whereas in C, you probably wouldn't take it on nearly so lightly. So we expect the compiler-generated code will improve markedly in the releases to come. The thing that I'm really looking forward to is we have a portable assembler, and I don't want to write the tables for those assemblers. So Russ has a tool that he's been working on that will read a machine instruction set as a PDF and print out an assembler instruction set. And it's actually been used to write the disassemblers that are there now, but we haven't coupled it to the front of the assembly. So the idea is that the manufacturer will either give you, or you're big borrow and steal, the PDF or perhaps the XML. There's an argument that ARM might give us an XML. Description of their instruction set, we turn a crank and you get a new assembler for a new architecture. That'll be pretty nice. That's the way computing is supposed to work. So, concluding, getting MFC with sounds like a fairly small thing, but I think it's actually one of the biggest deals. The 1.5 is a huge release. With C gone, the new garbage collector, the new scheduler work, Go Mobile stuff, this is actually a big, big numbered release. And so I think it's going to be one that will stand up, and it'll have a lot of new things in there. But getting rid of code is actually one of the biggest things in it. So we have code now all through the toolchain, all through the runtime. It's cleaner, easier to test, easier to profile. It's just going to get cleaner and faster as time goes on. We have this new unified toolchain that reduces the size of the binaries. You don't have multiple linkers and assemblers hanging around, and it's a lot easier to maintain now. And so we have a much more flexible toolchain, a much more flexible source code. And so things are just going to get better as it goes on. But as always, and from the beginning, portability is a key part of this. We want Go to be the most portable language out there. I think it already pretty much is, but we just want to make it more and more easy to move on. Thank you.
Thank you, Rob. And we have time for a couple of questions.
Nick, you should come and swap here.
So you use the phrase portable assembler a lot as you talked about the new linkers and assemblers. Are there any updates to from the Go core team about using that as a compiled and yet machine independent portable thing that I might keep around?
No, we haven't thought about that. Maybe. The assembler is not portable. 3D6 assembler and run it on an ARM. But the syntax is portable, and that makes a lot of the work of the assembler much easier. I mean, you're still talking about different instructions. It's not an intermediate representation like the IR and LLVM. It's still, this is assembler, even though it looks like 68,000. But the instructions in it are 3D6 instructions, and this is the ARM assembler, and its instructions are ARM. It's the same, and so most of the work of the assembler is in parsing. So it's just a portable language in that sense. If you like, it's portable language with different functions, you can go that way.
Is there a plan to put the compiler into a library so you might be able to JIT code at runtime?
We haven't talked about that. It's certainly something that's a lot easier to do now. There's a lot of, and I think we don't want to step in there while all this major linker work is going on to make C binaries callable from Go and vice versa, that kind of thing. But down the road, it might happen. It's not a small program. It's not a, it could be done conceptually.
Great. Well, thank you, Rob.
Cool. Thank you.
And next we have Aaron Schlesinger. I knew that I could do MC today, this morning, so I started looking something about him. The only thing I could find was that he likes soccer, but he calls it soccer, so I'm not really sure about that either. And he's going to be talking about concurrency.
All right, thank you guys. Thanks, Rob. Thanks, Andrew. It's a good start. Okay, I'm never gonna touch that again. Thank you guys for coming. I'm going to pop up the stack a little bit here, talk about some of the patterns in concurrency that I've seen, things that work for me in Go, things that I've seen work with my peers, and then more importantly, things that don't work. Everything I'm going to talk about today is my opinion, obviously, but I think many will agree here. So I do like soccer, thanks for saying, football, whatever. I've been a database engineer at Iron.io for like 3 months or 4 months or something. Been running for a little over a year and a half. Most of that before Iron was hobby projects and such. Contributed a little bit to a lot of things, I guess. A little bit of progression of the languages I've written. I still really love C++, just because I feel like it's more complicated than my life. So it's crazy. Anyway, Go here, I'm really happy with Go. And let's just dive into it. This title here was in the description of my talk. This is not a ding on Go at all. Go actually has some obviously very powerful primitives. That's one of the biggest reasons why I love it. Today, though, I'm going to discuss how I think we should be using these primitives responsibly. Many will disagree, some will agree, and I'd love to have the discussion. So I'm going to really briefly just go ahead. I'm going to touch on mutexes, channels, weight groups. We all know how to use them. I'm going to just lay out a little bit of the conventions that I use for them. I'm going to go into a little bit more detail on timeouts, how I do cancellation, how I use net context, which I'll show in a lot more detail if you haven't heard of it. And then there's a little special topic that's kind of near and dear to my heart, for select loops. I'll explain those in a lot of detail at the very end. So first of all, locks. They have a time and place. I've seen a lot of literature on when to use them, when not to use them. Best tool for the job has been thrown around a lot there. Hard to use. I just try to remember that. Everyone probably remembers that. When you don't have a good convention on how to use locks, things go bad. In a lot of code that I've seen that uses channels to communicate between Go routines and then adds in a lock, or vice versa, so they share memory by communicating and communicate by sharing memory, things go bad, or they can go bad. Generally, as we all know, share memory by communicating is preferred. So here's what I've sort of come up with Go specifically. There's not much here. Obviously, when you defer locking, even if it's a read-write lock, that's preferable. You don't have to remember, you can return, etc. The second two are basically just documentation points. That last part's important. There's conventions from other languages. Not saying we should all use them, because they're other languages, they're not Go. But the really important one here is the middle. Documenting ownership in your public interface is crucial if you're using mutual exclusion with locks. It's really, really painful as a caller to a library or as a library implementer to have to remember, oh, do I need the guy to own this, or do I need to own this before I call, or vice versa. To that point, if you can abstract that mutual exclusion into a high-level concept, some kind of reservation ID or something like that, very, very useful to do. Here's an example. There's a lot to read. I'm going to just touch on a few little points here. This is just some generic interface that it's modeled after some code that I've written at Iron. The basic idea is this is a map string to whatever value you want. And instead of passing channels back in this case, and instead of requiring mutex to be passed in, requiring ownership before functions in this interface, we just have this concept called a reservation ID. The reservation ID is just a little cookie that you get indicating ownership. Expired with this guy, and they can not exist. You can pass in a random old string and you'll get an error out. A few key points here. We talk about what's going to happen if you don't have a reservation here. We talk about what happens if you are able to acquire the reservation. We talk about what happens if the reservation is not already held. There's a few other things. The primary goal of this illustration here is to tell the user what's going to happen if they don't own it, what's going to happen if they do own it, and what's going to happen if the action takes place. The action in this case is the function call. Moving on to channels, I'm going to go through some of these primitives a little quickly here. We all know how to use channels in conjunction with Go routines. A lot of us know really well how to use select, and select is awesome as well. I read and heard somewhere from a lot of different people that channels and Go routines don't really matter unless you have select. I agree. Couldn't completely agree. Particularly for channels here, they're built in to Go for a reason, so let's try to use them by default. A lot of times when I've written programs, I fall back to the C days and I say, oh, let me get the pthread, link pthread. This is Go, there's no pthread, but we do have sync mutex. I try to convince myself why I shouldn't use mutexes or a read-write lock, and why I should use channels. Oftentimes for me, as a relatively new Go pro, half-ish years, I have to flip my thinking around a little bit. Thing about sharing memory by communicating instead of the vice versa. So, some conventions. It's really, really nice as a user of a library to know when I make a function call that takes in a channel or returns a channel, what's it going to do with that channel inside? I don't really want to have to go look in the code, although I do, but it's really nice to know that in the documentation. Show.org, very nice thing to have. Secondly, very similar point, when we enlist the compiler by using directional channels, we can get the compiler to tell us things about how our program will or will not behave right when we build it, not after running a writing test. So for example, the compiler will not let you close a read-only channel. And I'll show an example of what a channel or directional channel looks like in a second. Last 2 points there. We all know about close. When we're trying to read from a closed channel, we know how to range over channels, etc., etc. That one probably doesn't need a lot of explanation. The second to last one there, in case you don't know what a generator is a function that returns a channel but starts up a Go routine inside of it to interact on that channel. Really, in my experience, that's the only useful thing to do in a function that returns a channel. There are others, but that's a widely used practice. The reason is because if you return a channel from a function, and that function expects to do some interaction on the channel, you might get a deadlock. It might be very easy to get a deadlock, because if the function is doing something on the channel, you haven't gotten it back to listen or write to that channel. It's kind of ill-defined by default what's going to happen, because the library author hasn't told you what's going to happen. Go defines it very well, but the library author may not have. So here's a little bit of an example. This is taken from an ID tracking system for incoming service. It's a little bit, it proves, doesn't prove, shows the point a little bit. If you don't know, directional channel right there, it's a write-only channel, so that means watch changes will only be able to write on that channel. We talk about what happens if the request isn't reserved in watch changes. We talk about what happens in interaction on that channel that you pass to watch changes. You talk about specifically what happens in the interaction of that channel when an error is returned, a non-nil error is returned. And then a similar thing here. We talk about what happens with the wait group, we'll touch on in a second. We talk about what happens when that wait group will be done. We talk about what happens with the generator functions channel. We talk about what happens with the generator function's internal Go routine that interacts on that channel. That one's very important. And then finally, I've talked a ton about documentation. That part is over now. You don't have to read as much. I will focus a lot more on writing code. But this little point right here, let go.p empty. That's very important. It's kind of heartbreaking when I go to a Go.doc page and see nothing. I just see a bunch of documentation. That's really great. Go.doc is an amazing tool. When I don't have code, when I don't have documentation, I usually click into the functions. I look at the code. I understand how the library is working. But that takes on the order of 10 times more. It's an order of magnitude longer for me to understand how to use a library than it would if there was simple documentation. It doesn't even have to be as much as this or this, but just a little hint. What's going to happen with the channels? When do I have ownership? So on and so forth. That means the world. Just keep that in mind if you're writing any kind of reusable code at all, even if it's inside of your company, even if it's code that you don't think might be reusable or will be reusable, it still is very important, even for yourself, as you come back 3 days later. So on to wait group. A common use for wait group is to just notify when something's done. It's a good way to gather a bunch of Go routines together, as we all know when they're all finished. That's common, we know that. There's a couple other things that I've used it for before. I list them here. Is underappreciated in my opinion. When you are writing tests on functions or functionality that has a lot of concurrency going on, it's very useful to be able to make those tests deterministic. It sucks writing Go tests twice, having one failure and one success. I'll touch on a little bit more how to do this, but when you have that waits for a wait group to be done before it continues doing its testing, that can be very, very useful for you as a test writer, and obviously very useful for me as a test runner. So pretty simple explanation here. Sorry, pretty simple code example here. This is just notification inside of a for select loop, really just a for loop, endless inside of a go routine. It notifies the caller of start loop when the first thing has been done in the loop. So you can imagine this might be good in the test. If this is doing, for instance, some I/O, making an HTTP request to your handler, something like that, it can be really nice in the test for you to wait group.wait. Once the wait is returned, you're done. The first iteration of the loop is finished. Now you can check your handler. You can figure out, did it pass the right body? Is the body JSON decodable, et cetera, et cetera, et cetera. And that's instead of just time sleeping in your test and hoping that the sleep will return after the first iteration of that loop has completed. In that case, you're relying on the scheduler to schedule this go routine before your time sleep is up, and a few other things, so on and so forth. So now I'm going to move on. This is a little bit more complicated example. We all know about fan-in. If you don't know about fan-in, I really highly encourage you to go read Rob's talk here about concurrency. On slide 28, I think it's 28 through 32 or 33. You can just go to that link. Fan-in is a really, really powerful tool because it's a very easy way to how to do concurrency. We know Go is very good at concurrency. If you can do it, if the semantics of your program allows it, you should do it. There's no excuse not to. I define fan-in here, though, as both a code pattern that is shown in Rob's talk, and I'll show in a second, but also it's a series of steps that you can follow to take your sequential code and convert it into concurrent code. So there's another section that's really good under the Go blog. You can read under the fan-out, fan-in section of pipelines. Really, what fan-in boils down to here, though, is it's a wait group and a few channels. You put those two together in the right way, it's pretty understandable. So we'll start with our poorer function that doesn't really do any kind of concurrent computation. Imagine we just have a data store. We simulate the data store here by sleeping for a random number of milliseconds up to a second, and then we would just return a random integer. I'll prove to you that this does stuff. It takes a while. This might be the demo effect. Oh, okay. So yeah, we did a bunch of random integers. We took about 5 seconds, so that's about right. We slept randomly. Okay. Now there's a lot of bold here. These are the things we've changed in order to A, do this concurrently, and B, keep our public exported interface the same. So if you follow along here, that first function is just a utility. Basically added it so I can fit all the code on the slide. We're getting a wait group that adds 10 to it after we create it. And before we return it, we're getting a chan of int. Once we go into our loop, we're doing the same thing. We're doing 10 data store queries. Inside of each loop, we make a channel. Our new data store get function now takes in a channel and closes it after it sends the result back from the channel. So again, we're doing our random sleep to simulate our data store function. We're sending the result back, but the key here is the close signal. Remember I mentioned that before? It comes in handy here. We spawn a new little go routine to wait for our guide to be done and pass it back to the main channel being CH, the top. And then after we exit all of our loops, and actually there's a little bug here, I should have passed the C into here, apologies for that. At the end of our whole deal, we have one go routine that's waiting for all the guys to be done. That's waiting this WG wait. And then we close our main channel. Closing the main channel now, it allows us to have a pretty simple range here. The range will stop, as we know, once CH gets closed. And pretty simple. When we get each integer back, regardless of the order in which they come back, we put them into our slice, and now we can return them just the same as we did before. So bug and all, let's run this. So now we did our 10 in a little under a second. The bug effect here is that we're most likely going to be listening on the wrong channel. Actually, I take that back. We're not, because it's enclosed in the loop. Sorry. Demo effect again, but in my brain. Okay, so that's fan in, fan out. There's kind of a little list of steps. When I go back here, when I see something like this, when I see some I/O, for instance, almost always is I/O. When I see I/O happening inside of a loop, it's sequential. I immediately look at my lips and I go, okay, we can write a little bit more code here, but we get this huge speed up. We got an order of magnitude speed up here, 5x speed up. When I run this in Go max prox equals 4, it's about an order of magnitude. That's really great. This is not that much more code to get that done, so do it. I'm going to move on to production issues. This will be pretty similar to the fan in, fan out, but we're talking now about long-running systems, okay? Issues are always going to happen in we have flaky hardware, we're running in the cloud potentially, we've got bad networks, we're sending out across the internet, et cetera, et cetera, et cetera, disks, whatever. Some bigger shops, or you if you're really, really ambitious, you'll be able to write some infrastructure to test long-running systems. It's actually something we're working on right now at ION. If you have that infrastructure, use it. Test your long-running systems. See what happens long-term. Try to put way more data than it expects into it. Try and crash one of the nodes, et cetera, et cetera. But even if you can't, here's some ways to be proactive in your program to try and fail it gracefully. Try and make it a little bit more robust to those issues. So first of all, timeouts. This is a really, really term that I wrote to illustrate this. It's like starting a Go routine that listens on a channel that never gets sent on and then waiting for that channel. The reason I wrote it though is to illustrate here that if you don't time out on channel waits in your real production system, you might end up in something like this. This is kind of crappy to see if you have your little log aggregator at 2 a.m. You have to wake up and you see this. It's just like, I could have prevented that. I always think that in my head, that could have been prevented. Overcome it, just do a select. Remember selects? They're really nice. Just select on that channel and select on a timer. 2 cases in your select. And make the timer something reasonable. Have it time out after a second. A second's a long time, but at least it's not this. There's also one better we can do. That is net.context. There's a blog post on the Golang blog. Apologies for not including the link. But it's a big blog post on why net context, why Google uses it, why Google created it, and how Google uses it. Very great blog post. Just Google for it. Google is easy to find. I kind of cheated here though in my advocation for net context because in the talk description I said that everything would be done in the standard library. This is not in the standard library. It'd be really cool if it was, but it's not. But you could build it in the standard library in like a couple hours maybe, and that would include tests. It's so important here, in my experience, it's so important that I'm putting it in this talk, even though I have to make excuses to do that. So here's the interface, copyright and all. I hope I got that. So I took out all the comments. The comments are excellent. This is another good example for how to write comments. But essentially, this context interface can be constructed in multiple different ways. You can have a context that never sends undone. It's called a background context. You can have a context that you can cancel and then it will send undone. You can have a context that can time out it. And most importantly here is that you can build a tree out of these contexts. You can create a cancellation context out of another context that if the first context, the parent of the tree, then the child of the tree will also be canceled. You can imagine how in a large code base, that would really be nice. Caller and callee relationship. So let's talk about contexts as they might be in a distributed system. There is a Jeff Dean talk. I originally saw it at Recon 2013. He wrote a paper on it, I think beforehand. It's behind a paywall, so I couldn't include the link. It talks about a lot of practical things about how they run distributed systems at Google. You might imagine those are big distributed systems that they've run for a long time, so it's a pretty good guy to listen to. One of the interesting parts of this paper / talk is called hedge requests. Hedge requests are on the cover pretty simple. You just do a bunch of GET requests that they don't have side effects, they're idempotent, they don't do anything to a data store, so on and so forth. You do a bunch of them to a bunch of backends that are all identical, and when the first one returns, the simplified version, you just cancel all the rest of them. You get a lot more I/O, obviously, if you're running that backend over a network, it's a lot more network. He has a really good study that they did in real life on how it affects networks, what the trade-off is between the network and the speed of their services in the long tail. Encourage you to look at that. Rob showed a pretty good variant of that in the same concurrency patterns. You can see a theme here. On slide 50 of that same concurrency patterns talk. Encourage you to go look at that. I'm going to add on to that one extra part, which is the cancellation. So we talked about making a bunch of GET requests. It's great. You can just grab the first one that comes back. But what about the other ones? If the backends that you're doing a GET on are consuming resources, then it would be nice to be able to cancel them. If, for instance, they're doing some crypto, or they're accessing another backend, or they're doing a scan on disk, or something like that, if you're able to cancel them, you could potentially be saving a lot of resources. So here's what it looks like adding cancellation using net context. Let me just run this first. So what this is doing, it's saying, on the third line there, I will give you 10 milliseconds to get something done. We're going to start up 10 little getters here in Go routines. Get is a simulation of a net. It's going to sleep for some random amount of time less than or equal to 100 milliseconds. And then it's back on CH, on channel. It's going to send back its result, which is just a random integer. So you can see in this first little part, there's a chance that we might not get anything back. And by the way, the random number generators and all this are actually seeded with the current time. So we will actually get results back. So we're getting our results back, no result. Now we get a result. Now we get no result. We get a result. So you can see that sort of non-determinism. What would you do in a system like this if you start getting no results back? Well, you can do one or two things. You can wait for longer, which is just a little config value. We'll plug it into whatever config system you want. Or you can increase the number of gets. Both have trade-offs, but both are tunable. There's no extra code you have to write. If you do this right, you don't have to deploy any new code at all. You can just tune a value here and there. And then again, at the end here, the way that we're outputting this output, we've got our little select. We're either waiting on the channel to return for those, or we're waiting on the done. So the done will get sent after 10 milliseconds. One of these will happen before the other, and once that happens, we do our little print, and then we die. The get function will also list the done. If it gets a context done, it stops and it closes. That's it. The Go routine is dead. But there's a lot more we could do that he talks about in his talk and paper. One of the things he talks about is waiting until a 95th percentile latency and then start sending the other requests. That's when the off. That's when you should start trying to get other things. You can do that pretty easily with two contexts. One context for the first one, and for that first get, and have that context be set to the 95th percentile latency. If that context fires is done, and you haven't got a result back, create another context that's cancelable. Once you create the cancelable context, you can now issue that to n other gets. Once you've done that, if one of those returns, you're good. If not, now it's time to wake up at 2 a.m. or do something better. Hopefully do something better. The second thing, obviously we talked about canceling in-flight requests. Well, he goes a step further about sending the cancellation all the way down to the backend that the backend calls. Very simple. You just pass the context or some representation thereof across the wire if you're doing a network call. To a subsystem if you're doing it that way. The context can go anywhere inside of a Go program, and it always acts the same. It will always send on that done channel when the timeout happens or when it's canceled. And remember, we can build trees of it, so the guy who receives it, if it's a backend, that I've been calling it a backend, if the backend receives it, he can choose how long he wants to wait. And that's completely independent from the guy who called that backend. And then finally, this one I find pretty interesting. He talks about target-to-target communication. So if I'm sending out to 10 different backends, I can also send those backends some information about all the other guys who I've added. And those backends can coordinate amongst themselves. He doesn't detail how, but you can imagine some possible coordination algorithm that's going on back there. Those guys say, hey, I'm done. I'm going to tell all the other guys, in this case, all other 9 guys, that I'm done. And they shouldn't bother anymore. They can actually cancel each other. And you can obviously imagine we've got this context tool. Each one of those guys can context and send it to the other guys. So now they all know about each other. Now they can all cancel each other. Now we don't have to send those extra network calls over the wire to cancel the remaining 9. because they just do it themselves. And finally, putting all these ideas together, we talked about weight groups, we talked about channels, we talked about our we talked about not for select loops yet. We talked about context. For select loops are a way that I've seen to put them all together, and they can be very powerful when you put all these concepts together. So first of all, what are they? You can do a lot of things with for select loops. You can run an event loop or multiple event loops in different Go routines. You can do some kind of cleanup. This is not Go garbage collection, but it can potentially be compacting a log or recycling connections or so on and so forth. You can even do things like simulate an actor. It may not be a very popular thing to do, but you can do it. You can have a channel that you send to mutate state, and it can receive to get the result of the mutation, and so on and so forth. So the mechanics, you run a big loop in a Go routine. It's pretty simple at the top. Inside the loop, this is the select part of the for select. You select on 2 or more channels for each iteration. When you get a result, a send from one of those channels, you do it and you send the result back to somewhere. It doesn't have to be the caller, the sender of the channel, but it can be. And then sometimes for select operations can pass on the work that they receive to another guy and potentially pass a context onto that channel, for instance, result back to the original asker, if you will, of the work. So before I get into the code, a few patterns here. Again, for testability, it's very nice to have an ACK system. Your for select loop, it's going to be running forever, but it may not be very introspectable. It's very nice if you ask the for select loop to do some work. It may respond before the work is done, but it can be very useful, especially for your testing, but also for some things like I say, rate limiting and back pressure. It can be very useful to have an ACK. So for example, in testing, let's take that as a simple example. You submit your work to be done. It responds to you saying, I started, but you have an external channel or an external weight group potentially that will be done or be sent on once the work is done, maybe once it's started, maybe with some progress indication, and your test can make sure A, B, the right result has been sent back, C, it's been done in a reasonable amount of time, so on and so forth. Same thing if your for select loop is some kind of an event loop or a timer. If you're ticking, then you want to make sure to wrap your ticker in an ACK. I'll explain a little bit more about that in a second. Probably by now you know I'm a big fan of net context, so you probably want to use that for cancellation. Again, with these signals, for the last point here, it's very nice to have signals, again, once your loop is started, and most importantly, once it's stopped. In production, for instance, if you have a long-running select loop, perhaps it's doing something in the background as the result of getting some requests from the HTTP server. It'd be really nice to know if that loop is stopped, because your HTTP will still be responding to requests. The real work is not being done anymore. So it'd be nice to crash the server, send an alarm, whatever. So here's an example of a poller. We do a lot of queuing at IRMQ, so this would be a pretty good example for us. This is excerpt from some code that we have. This is a for select loop. You can see inside of a Go routine we have our for and we've got our select. This little guy is a simulation of a dequeue. So we're polling the queue every 5 milliseconds and we're dequeuing some data. Just says element with a random integer on it on the end there. And we're just doing that until we get our done. So if we get our done, we're in the middle of a dequeue. The next time, we're not going to do any more dequeues. You can imagine, extrapolate this out to any number of operations that need to be repeated. Checking a file, checking a timer, sending a message, doing cron, whatever. There could be a lot of different things here. A few other extra notes here. We've got 2 signals. We've got 1 for start, 2 for end here. And I'll explain what the deal is with both of those. We've got our 2 weight groups, 1 for start and end. We've got our channel that we're listening on. We've also closing that channel when for select loop dies. So if for any reason this for loop dies, doesn't look like it might here, you might be able to, you might end up adding something to it later, or so on and so forth. Both the channel will be closed, will be done. Those are 2 very useful signals that you may want to use. And then here's the little driver that I wrote for the poller. This one's actually runnable. You can see here, we're just going again. We're setting up 10 different pollers. We're waiting for the poller to start. We're consuming from the poller's channel. And when we're done consuming from the channel, we're done. Here, we're just doing the same thing, but for all the polars, we're fanning them all in again. And then here, since I didn't have enough room, print chan is just that range over the main channel. Once it's done, once the range returns, we're done. It just prints out everything until it's done. So here's the result from doing this run for 10 milliseconds. We just DQ'd a bunch of stuff until 10 milliseconds are up. Fairly straightforward, fairly simple. The real power here is in our for select loop. I've seen these things get expanded out to like 18 case statements, each one of which is responding to a signal from some other Go routine, responding to a ticker, something else. There's a million different things going on here. One of them I even saw, it was trying to add randomness by modding the Unix nano time by 6 or 8 or something like that. I don't know why, but it did it, and it's pretty easy to add in. It's just add another case statement. So then a couple of notes about this polar. I didn't put the ACK in for each individual operation. You go back here, each individual DQ operation, we don't have an ACK for it. You can imagine the ACK might be easily done with a channel send. But we also have a utility at Iron that adds ACKs to to timers and to tickers and a few other things. Those ACKs are implemented basically as just passing a func across the channel, and the guy in the select, it will just call the func. Whatever happens in the func happens, doesn't matter. The only contract is the func will never block. That allows us to stub out different tickers and timer implementation. It allows us to do counters in the func to count number of acts. It allows us to gather statistics, and so on and so forth. I'm leaving that as an exercise to the reader, but we might be open sourcing something fairly soon. And then I'm just going to wrap up. So Go has some pretty good concurrency stuff. We all know that. We've all seen it. I hope here that I've just kind of illustrated some better patterns on top of those. Maybe not better, but some patterns to think about at least on top of those. And I think that with things like this, more talks like this, if you guys can give them, more posts on new patterns, things like this, I think we're going to finally start building some new patterns and conventions on top of the great stuff we already have in Go. Really look forward to seeing that. So let's just see here. Use net.context, and this talk that I referenced is Rob's talk. It's called Go Concurrency Program, Go Concurrency Patterns. Really encourage you guys to go check that out. Thank you.
And we have time again for like 2 questions. Yeah.
I'd like please.
Oh, go ahead.
Hi. So I found your examples that execute code in serial to be a lot more readable than your examples that execute code concurrently. I was just wondering, how do you, when you have to decide between speed and simplicity?
It's a very good question. Usually, when I write something like I prototype it, I do the simple way, and it's really slow. It takes 10 seconds or something like that. We know about premature optimization, Rubal, Evo, and all that stuff. I wouldn't go and make something more complicated until you know you've profiled and you've seen that it's slow. If you find that you're really not doing that much I/O and it really doesn't take that long, don't do it. That's pretty much as simple as that. Does that answer your question?
Kind of.
Okay. It's a tough call to make because it tripled the size of the code or thereabouts.
I guess I was wondering, like, what is your decision process?
So my decision process really is just data driven. I just go in and I profile. I say, are these data store calls A, and B, how long are they taking relative to the rest of my program? It's a tough call to make to add more code, but my hope is that that pattern is recognizable enough to look across all the code base and see, hey, I know what this is doing, I know how this should look, and I can understand it. So it's kind of the best I can do for you.
Yeah.
Okay, thank you. And last but not least, there's Steve talking. Well, he used to work at MongoDB, and some months ago he joined Docker. He's managing now open source developer advocacy, and he's going to be talking about all the bad things he did with Go and how not to do them. Thank you.
Thank you. All right. First, thanks for staying. And for those who aren't staying, thanks for staying that long. It's fine. I'm not offended. I'd ask, we've been here a long time. Can everyone just stand up and stretch? Because I feel a lot of people here yawning and getting tired, and we all kind of need a little. Just don't leave, but like stretch, enjoy yourself. Okay. That felt good, didn't it? Good. All right. All right. So I'm going to talk to you about which honestly probably my most personal talk I've ever given. It's 7 common mistakes in Go and when to avoid them. Francesca introduced me working at Docker. I've also written a number of libraries and tools in Go. And the reason I highlight them is because I'm actually going to talk about these aren't common mistakes, these are my common mistakes that I've made in Go, and I've seen in other things, and maybe you're making them too. All right, so how do you feel when you see that? Does anyone else experience a bit of pain? We've been conditioned in this country, and maybe a lot of countries, from when we're very young, that failure is a bad thing, and that we shouldn't fail, and it experiences pain and anguish whenever we see something like this. And it's because it's so deeply ingrained in who we are that failure is something that should be avoided at all costs. This is a quote. It's might as well be from Yoda. It's not. But, it says, "Do you want to know the difference between a master and a beginner? The master has failed more times than the beginner has tried." And Ed Catmull, founder of Pixar, said, "We need to think about failure differently. Most people think mistakes are a necessary evil. Mistakes aren't a necessary evil. They aren't evil at all. They are an inevitable consequence of doing something new, and as such should be seen as valuable." Right? Go is a new language, relatively speaking. I think a lot of us are trying to do new things with it. Consequently, we're going to make mistakes. I personally make lots of mistakes, and there's a human tendency to want to cover up our mistakes, broadcast them, and I'm completely fighting that human tendency as I share my mistakes with YouTube and all of you in this room and anyone who watches this video later. Let me know who this is. It's also someone else. His name is Michael Bluth from a TV show Arrested Development. And if you watch this show, you get to this character because he doesn't want to make mistakes. There's another character who makes huge mistakes, who we laugh at and don't find as relatable. And hopefully by the contest here. So, and a lot of these are first, every one of these mistakes are Go specific. They're not general programming mistakes. They're most of them have to do with what I think are the 2 biggest new features. One is concurrency, and the other one is interfaces, which yes, some exist in other languages, but the way Go does them. So the first one is accept the interfaces. Now, I think it's important, and this is, I know this room's pretty Go savvy, but it's important to recognize that there's state and behavior. These are 2 fundamental principles of computer programming. Types in Go can express both state and behavior. State is equal to the data structure, and behavior equals the methods. Interfaces are one of Go's most powerful features. They permit extensibility. They're defined by methods, meaning that Go interfaces are behavioral. The adherence is satisfied only by behavior, not at all by the data structure, not at all by the state. I want to use an example from Hugo. If you haven't heard of Hugo, it's the fastest static site generator there is. Just a little story about this. We got a bug report, I don't know, 6 months ago. Someone was trying to build something with like 15,000 posts. And they said they tried every static site generator that there was. Most of them didn't ever finish. Hours later, had never finished. Most crashed. One finished in an hour and a half. Hugo finished in 10 seconds. So fast. Now most people also don't have 15,000 posts, but if it can do that in 10 seconds, it can compile your blog a lot faster than that. And this is all code examples from code that mostly I wrote. Don't do this. So what are we trying to do here? First, just setting up the stage in this slide. We've defined a new byte buffer and we're writing to it. There's nothing wrong with that specific part. But the next thing, what are we doing? We're grabbing the bytes and we're passing them into another function. And the signature of that function here that only accepts a byte slice. And what does that do? It creates a new reader. Right? So we've gone from something that satisfied a reader to extracting the bytes to creating another reader from it. Right? And you look at that and it seems pretty obvious, but if you look around Go code, you'll see things like this it's not just in my code. It's in a lot of other people's code too. So instead, right, what's the solution is pretty obvious here. All we do is convert it. Instead of taking a byte array, we're going to convert it to take an IO reader. And in doing that, we're taking an interface instead of a specific data type. And it's a lot more efficient. Two is piggybacking on that. It's not using IO reader and IO writer. And it's, if you look around different libraries, it's amazing how often writer simple and flexible interfaces for many operations around input and output. They provide access to a huge wealth of functionality, and I really want to underscore how much you can do with these two things. And they keep operations very extensible, and they're really simple. I mean, you can't define simpler interfaces than these. And light of time, you can read it, but the reader has a read method. That's the behavior. It's the behavior it from Cobra CLI, which powers Kubernetes. And so this line is actually one of the most powerful lines in the entire program. What this does is it lets you, for each command, like a command is like git clone, and clone would be the command. It lets you define a specific output for that. Because we've enabled it to be IO writer, it accepts a whole slew of different outputs, logging systems, network layers. There's a whole lot of different things you can do. In this case, we default to OS standard error, which again adheres to that. Viper is another tool. It's kind of the companion to. It lets you do configuration management, so it automatically reads JSON and TOML and the YAML files and environment variables and remote key value stores. And this is right from that code. This is the rest that didn't, but it was a great learning experience. So someone contributed this, read buffer config, and they passed in buff bytes buffer. Right? There's nothing wrong with this code. This code runs fine. It works really well. It's prescriptive about what's going to happen. Right? Much better is to an IO reader, which bytes buffer adheres to. It adheres to that interface. When we do, it enables our code to be much more extensive. Now people can pass a whole lot of this, whereas before we were very prescriptive. By the way, for me, if you have a question, just shout it out. Well, I don't know, raise your hand or something, but I don't want to wait till the end and then you forgot it. So I'm assuming no one's had questions yet. All right. I think a lot of this, I think it's obvious when you look at the slides. Hopefully you also think it's obvious. When you're writing the code, maybe it's not as obvious. So third one is requiring broad interfaces. So interfaces are composable. Functions should only accept interfaces that require the methods that they need. Functions should not accept a broad interface when a narrow one would work. You can interfaces made up from narrow ones. So use a couple examples. This is a Pharaoh FS library that I wrote specifically to make it so I could do testing better. Because with Hugo we do lots of creating sites and then destroying them throughout the test. I didn't want to write to the file system, but I didn't want to rewrite my code. So luckily, because the OS standard OS package defines all these interfaces really well, I was able to write a really thin library that lets you do neat things. Specifically, it gives you cross-platform memory-backed file system that's completely interchangeable with the OS package. So what do we do inside this? I've defined a file interface. a lot of different interfaces that it's composed of. And when you're defining a function, draw all this to say, hey, I'm going to include that broad interface. I'm going to include file everywhere, right? And if you've used other languages, a lot of other languages, kind of actually a pattern you look for. In Go, we don't want to do this. Why don't we want to do this? Why limit yourself? Well, what if I don't want to implement the entire file because I have good reasons not to, right? But now I can't use this anymore. So much better, we're only using the read function, so we should only use the reader interface. We shouldn't use that broad interface. All right, mistake 4, methods versus functions. I know this one trips up a lot of people, and it did me a lot when I first started. It would come from an object-oriented background. Really, what do the rest of you come from? Like, I know Robert does it, but some of you just don't raise your hands, I guess. Right, and we've learned that. We've been ingrained with that. A lot of us, that was the first programming environment that we really learned. And so we've been ingrained in how to use it. And part of that is, it's a lot really method heavy. And there's a natural draw for object-oriented programmers to define everything methods. But what is a function? So let's kind of. A function is operations performed on n number of inputs result on n number of outputs. The same inputs will always result in the same outputs. So functions don't depend on state. That's how they can adhere to that. What is a method? Method defines the behavior of a type. This is very specific. All right, so it goes back to the whole interface being behaviors. It defines the behavior of a type. A function it's a function that operates against a specific value, and it should use state. The whole point of it is to use state. It needs to be logically connected with that state. And functions can be used with interfaces. So methods, by definition, are bound to a specific type, whereas functions can accept interfaces as input. So example from Hugo, and this is an example of one that I think is really, Page is a major data structure within Hugo because it creates websites, so it creates lots of pages, and there's tons of methods on it, and there's a big draw to put everything down as a. And initially, when I wrote this function, shortcodes are kind of like template macros, and there's a draw to make this a method as well. It was a method, and I looked at it, I thought, why is this a method? It's not actually doing anything with that. It's using it, but it's using it as input. The same input, the same page every time, result in the not manipulating that page. And does that make sense? Am I explaining that reasonably well? A lot of people are nodding. Wow. That means you're even listening and paying attention. This is going pretty well for 9 at night. Right, so if you look here, we're really not manipulating it at all. We're just using it as if it was input.
But then you've got to decide which of those things on page are exported, returned. I mean, I'm not saying I like this pattern, but just you have to think about that.
Shouldn't you be thinking about what's exported? No.
Sure,
yes, you're right. You're totally right. Your point is valid.
But if extract shortcodes is not in the same package, you might have to, might be you need access to stuff like you're accessing another. It's just
a very valid point. Yeah.
So why would you not think of the shortcodes as a bit of the state of the page and say this is just a getter of that state?
So to repeat, the question is why would you consider something about the state with the page? It certainly is part of that, right? And you could make it to make it a method. The fact is, it's not changing that state at all, right? It's using its state. It's also using the string as input. So it's using multiple things as input here. The fact is, by definition, it's a function because the inputs and outputs, given the same inputs and the same outputs, it's always the same. Methods don't do that. Methods take inputs, often will change the state and result in an output. Maybe it's the same output, but that state change is going to be the difference. Now, you can include it, right? There's not a hard set to include it. Sometimes logically it makes sense to group things together around something, and often, in Go, a nice thing is you can actually have an empty struct or even a nil, and you can create methods on those things, right? But typically those are for logical groupings rather than treating them as methods. So really they're acting more as functions in that result. So mistake 5 is pointers versus values. So I've heard a lot of people, when I was learning Go, I heard a lot of people say, always use pointers, they're so much faster. Or always use values because maybe that's where they came from, right? If they came from a language like Java, they want to always use values because they want to copy everything. It's not generally a question of performance, but it's one of shared access. If you want to share the value with a function or method, then use a pointer. If you don't want to share it, then use a value, right? So generally, performance isn't the thing you should worry about. It should be about access and how you want to use it. So pointers versus value receivers is another question. I see a lot. People don't know what to do. A lot of the default answers, always use the top one. That's what generally people say because it's usually right. But again, pointer receivers are good when you want to share values, and often with methods you do. And because methods are manipulating things, so that's a very common thing. Remember, these are not safe for concurrent access, right? Because they're also using shared. Then you use receivers. If you want the value copied, then you use values. If the type is an empty struct, right, so there's no value to it, again, you should use values. And these are safe for concurrent access. So another example from a Pharaoh. In this case, right, we're calling close on a file. Right, why would we want that shared? Right, were you sending a pointer? Why? It seems because we modified state. Because we modified state. That's exactly right. And we want that uniform. Another example. This is from the time. Right, in the time package, it does use it uses methods, but it uses them on values, not on pointers. Why would it want to do that? Anyone?
Because time's ticking.
Because time's ticking. That's really, this one should be obvious. Well, thank you for being the brave person to shout out, Nancy.
It's taking a little long.
Yeah, time was ticking. All right. So mistake 6, thinking of errors as strengths. So when I started learning Go, all I heard about was all these complaints about errors. Go handled errors. And I think with all these conversations, people completely miss the point of what Go errors are and how powerful they can be. Yes, you don't throw, but you can do a lot of things with them. So first, a lot of people when they learn Go are surprised to find out error is not a type. What is error? It's an interface. It's a very simple interface. It's an interface that has only one behavior defined on it. It has an error method that returns a string. All right, so you can do a lot with that. So first, the standard errors are often sufficient, right? So you can call error new and provide a string, and it will create a value of type error of the interface that adheres to the interface error. You can also export error variables that can be easily checked. So from Hugo, this was some code in Hugo. We created error new, and we gave, pretty standard error there. All right, this is fine, it works, but how do you compare that? Usually people result in string comparison, and that's generally not the best way to do things. So better is to export it with a variable, and now we can check values, right? Checking values is a lot better than checking. I see this in code all over the place now. People are always checking strings and substrings to do it. This is another example of actually just the check. So that's the second part of that side. Now you can create your own custom error types. And there's 3 different reasons to do this. One is you can provide context to guarantee consistent feedback. Right? I see a lot of people creating errors that have lots of complex formatting in them. Don't do that. I'll show a better example. You can provide a type which can be different from the error value. Right? So the error doesn't, the error value and its own type can be 2 different things, and it's important, and you can do lots of powerful things with that. Last is you can provide dynamic values based on internal error state. So this is an example from Docker. Does everyone know what Docker is? Raise your hand if you don't know what Docker is. Well, I got you on that one, didn't I?
No, I use it. I was going to brag how much I use it.
All right, so this is from Docker, and this is a pull request we got recently. So Docker is a complex program, and we're trying to expand our errors and give better errors, and we're trying to prepare for internationalization in the future. At least someone who sent the pull request is. And so what we've done here is they've created this custom error type, which has error code and a message. Right? The message, if you look at error, this is how it adheres to the function. What is it doing? It's going to both the error representation of the message. The nice thing is you can check just the code. You don't have to look at the string message when you're using this. That allows you to do internationalization or various translations that the message value from the code itself. From the Go standard library, there's some really good examples. So this is one. These are just standard errors at the top two lines, and I cite them because it's important for the next slide. In this case, this is from the OS package. There's path error. That's a very explicit type. And if you look at the signature here, or the definition of it, what does it have? It has operation, it's got a path, it's got an error. And then look at how it creates it. It does the formatting for you in the error function. Right? So when you create this error, you're going to create it giving it 3 explicit things, and it's going to automatically format it for you. Now this is a function from inside the OS package. It's the write at one, and it returns an error. Right? Remember, error is an interface. So the first thing it does is it returns a standard error. Right? If f is nil, return a standard error invalid, which is a standard error. But if it's longer than that, it actually, and certain conditions happen, you're going to want a path error. Right? This explicit error type that we've defined earlier. What we're doing here is we're giving it the 3 parameters that we need to. We're not worrying about string formatting. Beyond that, you can do some pretty powerful things. In this case, this is a fake function that doesn't exist, but what we're conceiving of here is you might be writing something and say, you know what, if there's a path error, I actually don't care. I want to continue. I want to do something. Right? I don't care what the path error is. There might be values for path error. I don't care which one it is. I just want to see any path error. I'm going to handle it one way. Otherwise, I'm going to fail, and I'm going to call a fail. Another example here is this is a similar thing. We're checking the type. If it's a certain thing, we're going to be fine with it. In this case, we're actually checking for the specific value there too, right? So you can do a lot of things by checking with the types. Remember, the type can be independent of the error value itself, and that gives you a lot of power with errors. So they're a lot more than just strings. All right, mistake 7 is to be safe or not to be. First, you can't make everyone happy. You aren't a jar of Nutella. Right, so consider concurrency. If you provide a library, someone will use it concurrently. Here, it's going to happen. All right, data structures in Go are generally not safe for concurrent access. And values aren't safe. You need to create safe behavior around them. All right. So how do you make things safe? We just went through a lot of that with Aaron's talk, so I won't dwell on that. So with the Pharaoh, we were trying to map exactly the file system in OS. So this is how it looked initially when I coded it, and it worked really well until somebody put it in a Go routine. And when they ran a bunch of things concurrently, it blew up because it was trying to access the same at the same time. The solution is a simple solution. It's to use mutexes and add some locks around, right? And, all right, that's pretty clear there. Now, why are things unsafe, right? So this I gave the presentation earlier, and this section I got a ton of feedback on. It was mostly constructive. I had made a mistake, so this is me trying to improve them on that. Reality is there's lots of reasons to keep things unsafe. Safety comes at a cost. It also imposes behaviors on a consumer, right? So if we look, if we define a proper API, it allows the consumers to add safety as they need, and it lets consumers choose how they want to do it. They can use channels or they can use mutexes, whatever fits their situation. So this is back to the same slide. Why do we do it this way? Why do we put our lock in here? Because that's what the OS package does work concurrently, right? Because it delays things to the operating system, which lets it concurrently. So we wanted to model that behavior, right? So we didn't let it define above it, because in this case it made a lot of sense to implement it here because it's consistent with the OS package. However, maps, which are part of Go, are unsafe by design. Right? Often safety is unnecessary. I believe that's the argument for why they're still that way. It enables consumers to implement safety as needed, right? So I just showed an example. We're using a map. How do we implement it? We use the locks around it with mutexes. And the consumer of that can choose how they want to implement the safety. I also have, which I'm not going to go through because of time and because we just have a bunch of stuff on channels, but you could also use channels to do this. All right, so the biggest mistake is not making mistakes. All right, so again from Ed Catmull, failure is a manifestation of learning and exploring. If you aren't experiencing failure, then you are making a far worse mistake. You are being driven by the desire to avoid it. And it takes me back to, now who do I want to be more like? I want to be more like Joe, a little less like Michael, who makes a huge mistake. And that's my talk. Thank you.
So again, we have time for like 1-2 questions. Yeah.
Great, yeah, I want to go back to a couple of these. One was the overly broad interfaces or concrete types instead of interfaces. And then the other was pointer versus value receivers. It seems like both of those, or all of those could be caught through tools. And I'm wondering if you see that kind of eventually happening.
Certainly GoVet and other tools like that could help with a lot of these things. And in fact, I think GoVet does help with some of these things. Reality is, the reason I think a lot of these that I want to highlight them is A, they're not obvious. I don't think they're always obvious. B, a lot of them, it's not obvious when to do it, right? Sometimes there's a good reason to do one and sometimes a good reason to do it the other way. And there's a lot of context involved with that the code tooling couldn't help with because it's not going to know enough about the context of how you're using it, kind of the architecture that you have behind it. And again, these are things that I saw myself do wrong, and I use a lot of libraries out there, and I see it, it's being confused in a lot of places. I think the reason it's confused is it can be confusing because there's not always a clear answer. So I think yes, it can help with some things. On the other side, I think education and experience of using the tools more. I think how much I've learned in the couple of years I've been writing Go, and as I look through the standard libraries, which I use as inspiration on things, I see differences over the ones that are created later. Right? I think even the Go team is still learning a little bit about how this language works and how best to utilize it. And his head, so so is Rob, and so is Robert. So I think this is their creation. But just because your creation doesn't mean you know everything about it. I think all of us are starting to explore kind of different ways to do things. And the nice thing with the language, it's so flexible in the way that it is. It lets you express yourself in different ways. We're all still learning. So, all right.
Okay, so if there's no more questions, thank you so much to all the speakers. Round of applause for all of them. Thank you very much to all the sponsors, organizers, and there's actually still a lot of food. So before you leave, get some. And I think we have the venue for a little bit more. So if you want to stay, socialize a little bit more.
We probably ought to make our way now.
And also, okay, so there's no time to socialize. But while you're leaving, it'd be awesome if you take the bottles of beers that you have with you and you take them out. Thank you so much.